Part 3, we're going to finish here with the physical Earth. Now we're going to talk a little bit more about the actual processes and measurements that we use on the Earth. So the first thing is that when it comes to the science behind all of this that we're going to be talking about, that everything basically is comprised of two things that interact, matter and energy. So matter is just any material that occupies space and has a mass, which is pretty much everything on the planet. Atoms are matter. But matter interacts with energy. And as we'll talk about, energy comes in many different forms. But energy either changes how matter sits, it can change the state of matter from a liquid to a gas to a solid, or make matter do things. So as always, this is a really old joke. Remember, you matter unless you multiply yourself by the speed of light, then your energy. And that's basically what this is, E equals mc squared. This is a mathematical equation developed by Albert Einstein that says that in the universe, right, energy and matter interact, but basically that matter is never created nor destroyed. It's only changed by energy unless you apply so much energy that you can actually transform it. And it's also basically the equation that allowed us to build nuclear weapons. So let's put that in a real perspective. Let's look at matter. We'll start with H2O, which is what we call water. And water can exist as ice, like a glacier, water in a lake or rain, and then gas like clouds. So that's the states of matter: solid, liquid, gas. But if we add energy, and in this form heat from the sun, that transforms matter. So with solid water as ice, the molecules are very tightly locked together. They're bonded to a very strong, rigid matrix. It makes a solid ice. If you add energy in the form of heat, it loosens these individual bonds into smaller, more flexible ones, and ice becomes liquid, right? And liquid is not quite solid, but it's not as, loose as gas. If you add more energy, you break the bonds completely. Now you just have individual molecules of water, vapor, or gas. Conversely, if you were to subtract energy, the gas would coalesce into water and then eventually into ice. So some of the energy that we look at in physical geography is radiant energy, like sun waves. We talk about geothermal energy, or the energy of the heat from deep down within the center of the earth. Chemical energy. Certain forms of matter interact with each other to create chemical reactions. A great example is photosynthesis, which we'll talk about more in a little bit. So here's an example of how energy and matter interact and move through the systems of the earth. We start off with the sun, right? The sun breathes down and it causes water in the ocean to evaporate. So that's the energy, sunlight. It changes the state of water from liquid to a gas. That water then turns into rain, which falls down into rivers and carves canyons. So now the energy has changed from radiant sunlight energy to kinetic, or movement. The movement of the water erodes and carves these channels. That's kinetic energy. The water is turned back into a liquid matter state. We build a dam along the river, which stops the water, and we channel the kinetic energy of the water moving through pipes, which turn reservoirs, which turn turbines and create electricity. So we convert the kinetic energy to electricity, which is then fed through lines and plugged into an electric car. And now the car is moving kinetic energy again. So energy has never been created, only transformed. Matter has not been lost or gained, but just changes states. And as we are talking about the Earth, geo in geography, we have to start with this assumption that the Earth is not perfectly round. It's actually technically an oblate spheroid, which is kind of a weird term. It just means not perfectly round. 3 reasons. 1, the Earth spins like a water balloon. It's fastest at the equator. It actually bulges out as it spins around. So if you were taking a water balloon and you spun it, it'll do the same thing. Secondly, we know the Earth isn't flat because we have relief. We have differences in elevations. We have mountains and hills, and we have beaches, right? So if the Earth was perfectly round, there would be no mountains and there would be no valleys. It would be perfectly flat. And the last one, you don't need to worry about it too much, but not every rock on Earth has the same amount of gravity. Gravity is actually a reflection of density. Some rocks are denser. They weigh more per ounce. They weigh more per square foot, I'm so sorry. And so this is just kind of, magnified to make it look more obvious, but the Earth is actually slightly lumpy, or an oblate spheroid. If you cut the Earth in half at the equator and measure it, versus cutting the Earth in half from pole to pole, so vertical versus horizontal, you can see the difference here. The Earth is basically about 40 kilometers wider than it is tall. So it's a little bit bigger at the hips, you could say. And that's partly, in large part, due to the spin of the Earth. Now, 40 kilometers out of 12,000 is not a huge deal, but it is enough. And look at the difference. If you're standing at the North Pole, if you're standing on top of the Earth here, as the Earth rotates, you're really not moving. You're just kind of going like this. So you're really not moving. But if you stand at the equator, right, the time for the Earth to go around, you are actually moving in relative to other things at almost 1,000 miles an hour. So the big difference here, that's why the poles don't bulge. When it comes to relief, if you think about this, the highest point on Earth is usually considered Mount Everest. The tip right here is almost 29,000 feet above the level of the ocean, whereas the beach here at the Dead Sea in Israel, this is actually a small valley surrounded by mountains. This is actually 1,000 feet below sea level. So you have the variations between hills and valleys. And the last thing we'll talk about before I take another quick break is the physical systems. The book divides the systems that we're going to talk about here into four main categories. The atmosphere, which is the layer of gas that surrounds the Earth. The biosphere, which is all the life on the Earth. The lithosphere, the top level, basically the crust or first 100 miles of the Earth. And then the last part is the hydrosphere, all of the water, so the oceans, the rivers, the lakes, plus all the water that's frozen as ice. And you can see right here that the first 6 chapters of our textbook are all about the atmosphere. The next coming chapters, the biosphere, the lithosphere right here, and then the last one, lithosphere, and then the last one is actually the hydrosphere. So it kind of shows you the pattern that we're going to go through. What are some of the things that we'll be talking about? Just kind of an overview. So for instance, with the atmosphere, a lot of that we cover is weather and climate. The winds, the rains, the storms. And we'll talk about this more in detail, but just kind of ponder this thing. What is the difference between weather and climate? Don't have to answer right now. Just sit on it for a while. When it comes to the biosphere, we talk a lot about chemical reactions, specifically photosynthesis, right? Plants absorb sunlight, and the sunlight within the leaf of a plant causes a chemical reaction, which turns sunlight into chemical energy. In part 3, tectonic systems, right, the lithosphere, we're going to be talking about the crust, the outer surface of the Earth, and the energy that focuses that. The heat from the center of the Earth, geothermal heat, creates volcanoes and creates mountain building and builds high mountains. Conversely, solar energy, which drives snow, rain, and storms, produces water and erosion, which wears it back down. So geothermal energy builds the Earth's surface, but solar energy works to flatten it, and we'll talk a lot about that balance between the two. When it comes to part 4, which is the hydrosphere, we're going to focus a lot on erosion and deposition, how the water of Earth moves the stuff of the surface. It moves the soil, it sculpts it, it builds valleys and deserts and plains and prairies. And right, this is a change of the state of matter, evaporation. Water evaporates into the sky and forms water vapor, which then condenses to turn back into snow or rain, right? And then falls as precipitation. And I'm hoping that the idea that water can evaporate and condensate is not new to you. I'm going to assume we have that basic level of science. All right, I'm going to pause right here, and when we come back, we get to actually talk about, for the very first time all chapter, maps.